Hi everyone, lesson 4.3. We're almost halfway there in our last unit. This one is on second order homogeneous equations. So far we've looked at linear differential equations, and this is the first of two on second order equations. So this one's going to talk about homogeneous equations, which are where the right side of the equation equals 0. Okay. Non-homogeneous equations would be where that right side equals something, some number b. Let's say it's the number 5 or something like that. Okay, so that's the key difference when I say homogeneous. So don't think that it's something crazy. All it means is that there's 0 on one side. And these are going to focus on second order equations. In other words, if you remember back to our first lesson, it's where the highest order derivative that we have is a second order derivative, okay, or the second derivative. So when we look at these equations, we're going to start by looking at ones that have constant coefficients. So they have the form of some constant a0 times the second derivative, d squared y by dx squared, plus a constant a1 times the first derivative, dy by dx, plus a third constant, we'll call it a2, times just the normal function y, and that's all equal to 0. Again, it's equal to 0 because it's a homogeneous solution. Okay? To give you an example of it, just erasing what I wrote up here, this equation here, d squared y by dx squared plus 5 dy by dx plus 4y equals 0 is an example of a second order homogeneous equation. Okay? So the constants here, a0 would be 1 behind the second derivative, a1 would be equal to 5 behind the first derivative, and a2 would be equal to 4 behind the y function. Okay? To solve these, we're going to go back to doing factoring. We talked about factoring in our second unit when we talked about integration by partial fractions. Okay? So to solve these equations, we have a certain set of steps. I'm going to walk you through these steps. This is the first type of second order equation we're going to talk about, but you're going to see the steps are very similar regardless of which formula or which type of roots that you're going to see we have. So we're going to start with that same example that we had. D squared y by dx squared minus 3 dy by dx plus 4y is equal to 0. Okay, so the same example I gave you in the previous slide. Now, one thing I want to do before I move on is I want to tell you that I like to denote our derivatives in this form. Dy by dx is d squared y by dx squared. Your textbook uses two other ways to also note it. So they will note questions that way. But they also use y double prime, which means the second derivative of the y function, and y prime to denote the first derivative. They also introduced this new notation, which I'm not a fan of, because why do we need a third one? But it's there. And I'm showing you these because you'll see them written this way in the practice exercises, but you can always rewrite them in the form here, or whatever form you're comfortable with. But the third method is they simplified it and wrote capital D squared y. Okay, so that is the same again as writing d squared y by dx squared. And for the first derivative, they just wrote dy. Again, that's the same as dy by dx. So all of these notations are exactly the same. Okay, so keep that in mind. When you read the practice exercises, don't think that because they're written differently that the questions are any different. And you're free to calculate your solutions using any of the three, but just know that I will follow this format here. And I like to stay consistent in how I do these questions in your lessons. The big reason for that is just so that it's not confusing when I switch back and forth between notations. Okay? So once you have it written in this form here, what you do is you replace all of these differentiation terms with m. And that m has an exponent that matches the order of the term. In other words, you write m squared for a second order, d squared y by dx squared. You write just m for the first derivative, dy by dx, and nothing for y. Okay, you're just assuming that the value is 1. So if you do that, this changes to m squared, okay, or I guess I'm writing it. It changes to this form here. And all I've done, I don't know why I decided to write it a second time, all I've done is replace these d squared y by dx squared terms with m's, okay? So using this, what you notice, or you may have noticed, this is actually a quadratic function, okay? Remember your quadratic form you might have saw, ax squared plus bx plus c is equal to 0. This translates it into a quadratic equation. And with quadratic equations, when they equal 0, you can find the roots of them by factoring. Okay? In this case, if you remember back to factoring, we talked about it in our second unit. I also have another video that talks about factoring. So if anybody wants it, I can also post the link to that as well, or you could find it on my YouTube channel. So when you're factoring in this case, remember, when the coefficient behind the first term is just 1, then what you're looking for is you're looking for two numbers that multiply to this value, positive 4, and add to this value, which is positive 5. So the two factors for that are plus or positive 4 and positive 1. So you can factor as this becomes m plus 4 times m plus 1. And that equals 0. So our next step is to factor and find the roots of the function. So if we do that, remember, what we're trying to do is make the left-hand side equal the right-hand side of the equation. And to do that, one of these sets of brackets has to be 0. So either the first set, m plus 4 equals 0, so m is negative 4, or the second set of brackets, m plus 1 equals 0, so m must be equal to negative 1. So we know that our two roots are negative 4 and negative 1. And what we do with that is, you saw that we replaced the differentiation terms with just m. But what we do is we take these roots and we plug them into general solutions. These are solutions that have been developed specifically for these types of differential equations. And the general format of the solution is that y is equal to some constant, c1, times e to the exponent of the first root times x, plus a second constant, c2, times e to the exponent of the second root, m2, times x. And it doesn't matter what order these are in. Okay, so it doesn't matter if you flipped them and m1 was negative 1 and m2 was negative 4. It doesn't matter. All it matters is that once you follow these steps and you find the roots, you plug them into this formula. Okay, so in terms of our question that we've been looking at here, our final solution would be our c1 times e, and our value for m1 is negative 4, so it's negative 4x, plus c2 times e to the exponent of negative x, because our second root is negative 1. Okay, so this set of steps you're going to see in this first instance is for neat and tidy solutions that we can factor. But the steps will largely remain the same as we look at different types of roots, like if the two roots are the same root or if they're complex roots. Okay, and if you remember back to actually talking about quadratic equations, what you see here, okay, is a parabola that looks something like this. When the roots are the same, the parabola changes, and what it means is that the base, or what I call the vertex of the parabola, touches the x-axis. And if they're complex roots, which is our third case today, the parabola doesn't actually cross the x-axis, okay? Because remember, these roots are actually solving for when the function crosses the x-axis, okay? Again, Those are just to re-familiarize you with, the whole quadratic equation. Even though these are differential equations, we're still using that math to solve them, okay? So let's look at a couple of examples. So I'm going to do, 3 examples, each slightly different, to show you how to solve these. And then we're going to go into our 2 different cases where the roots are repeated and when we might have complex roots. So our first example is to solve d squared y by dx squared minus 3 dy by dx plus 2y is equal to 0. This is already in the format where we have everything on the left-hand side and the right-hand side is 0. So our first step we don't have to follow. Our second step is that we now have to replace the d squared y by dx squared with m squared and the dy by dx term with m. And our y term, you can consider it, all we're doing is replacing it with 1, okay? I usually just omit it because then it just becomes a constant, but you can think of it either way. So replacing those, we get m squared minus 3 times m plus 2 is equal to 0. So now that we have an equation that looks like a quadratic equation, we can now solve it by factoring. Okay, so in this instance, we're looking for numbers that multiply to positive 2 and add to negative 3. So if we want to think of that, negative 2 and negative 1 multiply to positive 2 and they add to negative 3. So we're left with m minus 2 and m minus 1. Okay, you can check these by multiplying it in, okay, or distributing each of these factors. It's totally up to you. But once you see me do multiple examples in different types, I think it'll come back to you pretty quickly. So now we see here that we have 2 instances. Either the first bracket, m minus 2 is equal to 0, in which case m is equal to 2. Or the second instance, m minus 1 is equal to 0, so m must be equal to 1. So our 2 values of m, we'll call them again m1 and m2. It doesn't matter what order they're in, like I said previously. m1 and m2 are 1 and 2. So remember, our general form, when you have 2 distinct roots like this, I'll emphasize that, is equal to our constant c1 times e to the first root, m1 times x, plus c2 times e to the m2 times x, so the second root. Again, this is for 2 distinct roots that we're seeing here, okay? So different numbers of 1 and 2. So if I substitute those values in, I get that y is equal to c1 times e to the x, because m1 is 1, plus c2 times e to the 2x. Okay? And you can see here that my solution is in the opposite order as what I came up with going over this. And like I said, that's okay. It doesn't matter what order they're in. So I place the roots in a different order, but again, it doesn't matter. Okay? Because these values behind it are constants. In our third example, I'll show you how to solve for those constants. Okay? So our second example, this case, we have a constant behind the second derivative term. So our factoring becomes just a little bit different here. So we have to solve 3d squared y by dx squared plus 8 dy by dx plus 4y is equal to 0. So again, remember, d squared y by dx squared, we substitute in m squared. dy by dx, we substitute in m. And for y, we simply substitute in 1. So if we do that, we have 3m squared plus 8 times m plus 4 is equal to 0. So when we have a constant behind the squared term, the factoring is just a little different. So instead of just multiplying to this value here, you have to multiply those two numbers together. So 3 times 4 is equal to 12, the first and last term. And now instead, you're multiplying to give you 12, positive 12 in this case, and adding to positive 8. So for that, we have positive 6 and positive 2, because positive 6 and positive 2 multiplies to positive 12, and they add to positive 8. So remember, instead of writing them with brackets, when we're factoring, when we have a number behind the squared term, we have to break up this middle term using our two factors. So we have 3m squared plus our first factor, which is 6m, plus our second factor, which is 2. Oh, that's a bad m, 2m, and plus 4. Okay, so that's still 6m plus 2m adds to 8m. But this is how we break it down first. Then what we do is we group the first two and the last two terms, and we factor them. Okay, so we start, in the first two terms, we can remove a 3 and an m. So we have 3m. In our remaining terms, we have an m left in the first term, and just a 2 in the second term. For the second grouping of terms, we can take out a 2. We can't take out an m because there's no m in the very last term of 4. So we take out a 2, and what we have left with is m plus 2 equals to 0. So you can see that both the first and second terms that are factored now have a common factor of m plus 2. So we can factor the m plus 2. And what we're left with are the terms that are remaining outside of the brackets, which is 3m plus 2. So just a couple more steps when the coefficient is not just 1. So now what this means is that either m plus 2 is equal to 0, or m is negative 2, or 3m plus 2 is equal to 0. So solving this, we get 3m is equal to negative 2, or m is negative 2/3. Okay? So substituting in, remember we have our basic form, because we have two distinct roots, negative 2/3 and negative 2. So we have y is equal to c1 times e to the first root times x, plus c2 times e to the second root times x. So substituting in our values, we get y equals c1 e, the first root, which is negative 2 times x, plus c2 times our second root, e to the negative 2/3 times x. Okay, so the method remains the same. Okay, just what changes in every one of these, and you'll see these in my next two cases as well, is the way you factor changes slightly. Okay. Okay, so our third example is going to be the same, where we solve for the roots. But in this case, what if we want to find a particular solution? Remember, our particular solution is where we don't just have constants C1 and C2. Okay, so we actually solve for the constants. Now, since there's two constants, we actually would need to know two separate points. Okay, so I've provided those 2 points as well as our equation. So let's look at solving it. So we have to solve 5 d squared y by dx squared plus 12 dy by dx plus 4y is equal to 0. And we have the points when x is 0, y is 0, and when x is 1, y is 1. Okay? So our first step remains the same. We replace d squared y by dx squared with m squared, dy by dx with m, and y with just a 1. So if we do that, we get that we have 5m squared plus 12m plus 4 is equal to 0. So in this case, remember we have a value before the m squared term of 5. So we have to multiply the 5 times the last term, which is 4, and that's 20. And then we have to figure out numbers that multiply to positive 20 and add to positive 12. And those numbers are positive 10 and positive 2. So I rewrite this as 5m squared plus 10m plus 2m plus 4 is equal to 0. Now, factoring the first two and the last two terms separately, we can take a 5m out of the first term, and we're left with m plus 2. And again, we can take a 2 out of the second term, just like our last example, and we're left with m plus 2. So what this means is this factors to 5m plus 2 times m plus 2, which is equal to 0. So what this is saying is that either 5m plus 2 is equal to 0. Solving this, we get 5m is equal to negative 2, or m is negative 2 over 5. Or we have that m plus 2 is equal to 0, so m is equal to negative 2. So we can use those roots just like we did. Remember our basic formula, y is equal to c1 e to the m1 times x plus c2 e to the m2 times x. And if we substitute in our values for m1 and m2, we get that y is equal to c1 times e, and our first root is negative 2 over 5, plus our second root, c2 e to the negative 2x, substituting in our second root. So now having this formula, we can solve at each of these points here. Okay. Again, because we have two constants, c1 and c2, we're going to need to know 2 points to solve it. So I'll put a line here for us to solve. So we'll start with when x is 0 and y is 0. So starting with our equation, it means that y is 0. So we have 0 is equal to c1 times e. In this case, it's negative 2 over 5 times 0. Plus c2 e to the negative 2 times 0. Well, anything times 0 is 0. And if we have an exponent, anything to the exponent 0, remember it's always 1. So going back up here to my items to know, e to the exponent 0 is simply 1. So if both these terms are 1, what we're left with is that 0 is equal to c1 plus c2. Or if we want to solve for one in terms of the other, we get that c1 is equal to negative c2. Okay? So our second function is when x equals 1, y is equal to 1. Right? So doing that again just directly below it, we get that 1 on the left-hand side is equal to c1 times e to the negative 2 over 5 times 1 plus c2 e to the negative 2 times 1. So remember, we know that c1 is equal to negative c2. So we have to solve for one of these two equations. We'll solve for c1, just because it's the positive one here. It seems to be a little easier. So to do that, what we have to do first is move this function with c2 to the other side. So we're left with 1 minus c2 e to the negative 2 times 1 is just negative 2. And that's equal to c1 times e to the negative 2 over 5. Okay? So to solve for c1, we have to divide both sides by e to the negative 2 over 5. So they'll cancel here. And we get that c1 is equal to 1 minus c2 e to the negative 2 divided by e to the negative 2 over 5. So one thing you'll likely see is that the start of this is very simple when we're not solving for a particular solution. The bulk of the work in these questions, when you're finding a particular solution, is actually doing this algebra to solve for the constants. Okay. So in this case, substituting it in, remember our original equation we had here, C1 is equal to negative C2. We'll substitute in for C1. I like to kind of compartmentalize these so that you can follow along better. So we have 1 minus C2 e to the negative 2 divided by e to the negative 2 over 5. Substituting in for C1 is equal to negative C2. So to solve this, my first step is going to be to move this e to the negative 2/5, okay, to the other side. I do that by multiplying both sides by e to the negative 2 over 5. So after 1 minus C2 e to the negative 2 is equal to negative C2 e to the negative 2 over 5. So now, okay, to solve for this, we move the C2 to the other side of the equation. And we're left with 1 is equal to negative C2 e to the negative 2 over 5 plus C2 e to the negative 2. So now we can actually factor out a C2. Then we get 1 is equal to C2 times our first item, which is negative e to the negative 2 over 5 plus e to the negative 2. Okay? So substituting, or sorry, to solve for C2, we now have to divide both sides by this big function here in brackets. Again, I'll circle it. And if we do that, we get that C2 is equal to 1 divided by what we have left here, which I like to put the negative second, e to the negative 2 minus e to the negative 2 over 5. So remember, C1 is negative C2. So C1 must be equal to the negative of C2, which is negative 1 divided by e to the negative 2 minus e to the negative 2 over 5. Okay, so you could, I guess in theory, use your calculator to find e to the negative 2 or e to the negative 2/5. It's up to you. I just, the algebra seems more difficult, but this is kind of more of the exact answer if you do it this way. So if you substitute these in, you end up with y is equal to, you can see that the constants are the same value. There's just a negative that's different. So you can actually factor out that whole piece to make this a little simpler. So you get 1 divided by e to the negative 2 minus e to the negative 2 over 5. And that's multiplied by what we have left going back to our original equation here. Okay, so C1, if you remember, we still have a negative left. So C1 is negative e to the negative 2 over 5 x plus our second function e to the negative 2x. Okay, so all I've done here is I've substituted in the values of C1 and C2. The one step I skipped, and the reason I did was because I was running out of space here, was that both these constants have the exact same term. 1 divided by e to the negative 2 minus e to the negative 2 over 5. The only difference is that C1 has a negative at the top. So what I did to simplify it, again because I was running out of space, was I factored out that 1 over e to the negative 2 minus e to the negative 2 over 5 term, just to make it a little bit simpler. Okay? So again, what I want to stress in this is, finding the particular solution involves far more work just because of the algebra. But the method to solve it, regardless of what you're given, is still the same to find the general form of the equation, which is what you saw here on the left. So our solutions so far, you saw in the last 3 examples, are what I call neat and tidy. And what I mean by that is that the roots were simple numbers. And more importantly, I talked about them being real and distinct, so not complex numbers. And they were distinct, meaning that they were different, okay? So you had different roots. The next case I want to look at is if the roots are repeated. Okay, so remember, going back to when I drew the graph, what that means is that the roots of the function actually touches the x-axis if you're talking about parabolas or quadratics. So it's only one root that would come out of this expression. So for repeated roots, we only have to adjust our methods slightly. And if you can remember back to partial fractions, integration by partial fractions, we talked about repeated roots there. A very similar thing is going to happen here in our general solution at the end. Okay. I just want to kind of preface it before we start. So for repeated roots, we start off by doing the exact same thing. We make sure the equation is in this form. So everything on one side of the equation, your second derivative term, your first derivative, and then your just term with y, or whatever the function might be. And it's equal to 0, because it's a homogeneous equation. Homogeneous, I guess I kind of use those interchangeably. Your second step, again, still the same. Replacing the d squared y by dx squared term with m squared, dy by dx with m, and the y just is, you replace it with a 1. Okay, so none of these have changed. Again, finding the roots, nothing changes. So in this case, if you're finding the roots, if you have m squared plus 4m plus 4 equals 0, remember you're multiplying to positive 4 and you're adding to positive 4. And what does that is positive 2 times positive 2. So factoring that, you get the same root, m plus 2 times m plus 2. Meaning that, remember when we looked at either m plus 2 equals 0, so m is negative 2, or the exact same thing, okay? M plus 2 is equal to 0, so m is negative 2. So the fact that they have the same roots, that means that our roots, which we call m1 and m2, are both negative 2. And our general form of the equation doesn't change. The only thing that does change is because the roots repeat, the second term is multiplied by x. Okay, so remember the original version was y equals c1 e to the m1 times x plus c2 e to the m2 times x. Now we've added this x term in here, okay, which you can see I've color coded it to make it a little bit easier. So the reason for this is, remember back to when we talked about integration by partial fractions. When we had repeated roots, we had to add an x like this. And the reason that we have to do that is so that these can be distinct, right? It's not the exact same function, they're different functions. So in the case that we have here, we have c1 times e to the negative 2x plus c2 times x times e to the negative 2x. So with that, we can factor, okay, we can factor out the e to the negative 2x because it's in both functions. And the other form you'll see it in is, as it's factored, the function e, so e to the negative 2x, and it's multiplied by the constant c1 plus the constant c2 times x. Okay, so that's the only major difference, is that adding that x piece in here when the roots are repeated. Right? So we're going to go through just one example with repeated roots because you saw everything else in it is the same, right? Everything else is the same as if we solved those real distinct roots in our first case. So in this case, we have to solve d squared y by dx squared plus 6 dy by dx plus 9y is equal to 0. So we start with our same starting point, d squared y by dx squared. We replace with m squared. dy by dx we replace with m, and y we simply replace with a 1. So doing that, we get m squared plus 6m plus 9 is equal to 0. So our numbers have to multiply to positive 9 and add to positive 6. And to do that, we get positive 3 times positive 3. So we're left with m plus 3 times m plus 3 is equal to 0. So you can see we have the same root twice, or repeated roots. So that means that m plus 3 is equal to 0, or m is equal to negative 3 in order to make this equation work. So our roots are both negative 3. So starting with our form, remember the difference is we have c1 e to the m 1x plus c2 times x, don't forget the x, e to the m2 times x. So since m1 and m2 are the same, they're both negative 3. We get y equals c1 e to the negative 3x plus c2 times x e to the negative 3x. Okay? If you want to get to, the most simplified answer, you can factor out the e to the negative 3x. And we get y is equal to e to the negative 3x times c1, which is all that's left in the first term, plus c2 times x. Okay, and you'll see that this format, this final format, will be how you'll often see the repeated roots shown. Okay. Our last case is where we have complex roots. So remember, going back to drawing our graph, when we have quadratic equations, it means that the parabola sits entirely above the x-axis. So there's no roots, right? So when we solve this, we're actually not going to get a real number. We're going to get a complex number. The reason for that is because this root term, which is known as the discriminant, has a negative number under the root sign. So remember, to remove a negative number, let's say we had the root of negative 1, we write it as just I. Sometimes you might see it written as J, but either or, they're kind of interchangeable. So you kind of substitute that in, and that becomes a complex number. So with complex roots, we actually have to use the quadratic roots formula, okay, which I've provided here. As you remember back, it's negative b plus or minus the square root of b squared minus 4ac over 2a, where a, b, and c are ax squared plus bx plus c equals 0. Or in our case, using m, we'd have a times m squared plus b times m plus c is equal to 0. So that's the constants that you sub in to the quadratic roots formula. The trick is we're going to use the numbers in the root formula without solving them using your calculator. Okay? So to solve this, again, I run through the steps. The first step remains the same. You have to make sure that you have all the terms on the left-hand side, first derivative, second derivative, and the function of y, and it equals 0 on the right-hand side, again, to be a homogeneous second-order equation. So our example we're going to use to show you this is d squared y by dx squared plus 2 dy by dx plus 4y is equal to 0. Same as before, our next step is we're going to replace the d squared y by dx squared, dy by dx, and y terms with the appropriate m terms. And we're left with m squared plus 2m plus 4 is equal to 0. So now remember, for complex roots, we have to use the quadratic roots formula. You can't factor them. You're free to use quadratic roots to solve the previous cases as well. It just takes longer to do those calculations when you could just factor it just as easily. It's up to you. Okay? So if we use the quadratic roots, in this case, we have that a is equal to 1, b is equal to 2, and c is equal to 4. So if we substitute them in to our quadratic roots formula, we get negative 2 plus or minus the square root of 2 squared minus 4 times our a and c terms, 1 and 4, divided by 2 times our a term, which is 1. And you can see here we're left with negative 2 plus or minus the root of negative 12. So remember, in order to remove that, we take the -1 out of the root by setting the root of -1 equal to I. That makes it a complex number. So if we simplify this, the first term we get is -1 because we have -2 divided by 2, plus or minus the root of 12 times I, which means it's complex, divided by 2. So we get to this point and we have to leave it like that because we're going to use each of those two numbers in our final solution. Okay, so our first number is the -1, the number before the plus minus sign. The second number is the number that's attached to the complex piece, which in this case is root 12 over 2. And the notation that we use is alpha for the first term, which is -1, and beta, which is root 12 divided by 2. Okay. Now, in our instance that we have here, our general form looks a little bit different. Because we have complex numbers, we add a sine and a cosine piece. Okay. So we use those values. Remember, we have alpha is -1 and beta is root 12 divided by 2. And this is our basic form. Okay, y is equal to, in this case, e to the exponent alpha, the first term, times x. And then that's multiplied by a constant c1 times the sine of our function. Okay, and this time we have our second term, beta times x, plus our second constant c2 times the cosine of beta x. Okay. Each of these formulas for all three instances will be provided to you for your test. So now if we simply substitute in our values for alpha and beta, we get that y is equal to e to the -x times c1 sine of the root 12 over 2 times x plus c2 times the cosine of root 12 over 2 times x. Okay, so it's a little bit different in terms of using quadratic roots formula, but at the end, you still have all the same pieces. You have the constants and the e terms. The difference is we add a sine and a cosine. All right. Okay, so let's look at one example with complex roots. Solve 2d squared y by dx squared minus dy by dx plus 2y is equal to 0. So again, we're going to substitute in d squared y by dx squared is equal to m squared. dy by dx is equal to m, and y is simply 1. And what we have is 2m squared minus m plus 2 is equal to 0. So in this case, we know that a is equal to 2, b is -1, and c is also 2. So using our quadratic roots formula, we get -b plus or minus the square root of b squared minus 4ac divided by 2a. Again, I will also provide you the quadratic roots formula. So substituting in our values, we get negative times b, which is -1, plus or minus the root of -1 squared, minus 4 times a, which is 2, times c, which is also 2. And that's all divided by 2 times a, which is 2. Okay? So substituting each of these, or simplifying these, I should say, we get negative of -1, which is +1, plus or minus, simplifying this root, we get 1 minus 16, or the root of -15, over 2 times 2, which is 4. So writing this in terms we've seen before, we get 1 over 4 for the first two, plus or minus, we get the root of 15 times I, remember returning it complex, divided by 4. So we know now, looking at this, that our value for alpha is our first term, which is 1 over 4, and our value for beta is our second term, root of 15 divided by 4. So knowing these, remember our basic form of our formula, y is equal to e to the alpha times x times c1 sine of beta times x plus c2 cosine of beta times x. Okay, it doesn't matter if you put cosine or sine first and you have c1 cosine and c2 sine, it doesn't matter, okay, because those are just constants, so keep that in mind. Substituting in our values, we get that y is equal to e to the 1 over 4 times x times c1 sine of root 15 over 4x plus c2 cosine of root 15 over 4x. Okay, so similar format, just the extra steps of doing quadratic roots. Okay, so that was all I had for this lesson. All right, this covered two sections, 31.7 and 31.8. If you do have questions about these exercises, bring them to our tutorial sessions or send me a Teams message or email. Thanks, everybody.